All right, everyone, welcome. Have you ever really stopped to think about it? You take a tablet for a headache, and after a while, the pain is gone. But what actually happens to that medicine inside your body? Well, today, we're going to follow that tiny pill on its incredible journey right from the moment it goes in to the moment it comes out. So let's begin. So, you've popped that pill, now what? The drug goes in, it does its magic, but then what's the exit plan? It can't just hang around in your system forever, can it? Your body needs to clean house. And understanding how it does that, well, that is the very heart of pharmacology. It's absolutely fundamental. Okay, so right away, our body faces a huge problem. You see, most drugs are what we call lipophilic, a fancy word that just means they love fat. They're essentially oily. Now, this is actually good for them. It helps them slip through the fatty membranes of our cells to get to work. But, and this is a very big but, when it's time to leave, it's a disaster. Why? Because our body's main disposal system, the urine, is almost all water. And as we all know, oil and water simply do not mix. So how does the body solve this puzzle? It has a brilliant strategy. It's called biotransformation. You'll often hear it called drug metabolism. The whole goal is really quite simple, almost genius. The body's chemistry labs take that oily, fat-soluble drug and transform it into a water-soluble or polar form. Once that's done, flushing it out in the urine is easy peasy. Without this process, believe me, some drugs could stick around in our bodies for a dangerously long time. So where does all this amazing chemistry happen? Well, it happens in the body's main chemical factory, the liver. Let's take a look at the liver's very clever two-step plan for dealing with these drugs. Now, this diagram here, it shows you the entire game plan. A drug comes in, it goes through what we call phase 1 metabolism, and then it's followed by phase 2. Now, sometimes a drug can actually skip phase 1 and jump straight to phase 2 if it already has the right chemical structure. But no matter which path it takes, the end goal is always the same, to create a final metabolite that's the transform drug that's all ready to be kicked out. Let's break this down with a really simple analogy. Imagine the drug is like a smooth, slippery suitcase with no handle. It's tough to grab, hard to get rid of. So step 1, or phase Y, is where the liver's enzymes come in and attach a handle to that suitcase. Got it? Now we have something to grab onto. Then comes step 2, phase 2. A different team of enzymes comes along, grabs that new handle, and attaches a big, bulky, water-soluble tag to it. That's it. First the handle, then the tag. A very neat two-step process. Okay, let's get a little more technical for a moment. Phase 1 reactions are called functionalization. That's the scientific name for adding that handle. Now, here is a crucial point you must remember. The resulting metabolite, the drug after phase 1, can sometimes still be biologically active. In fact, sometimes it can become even more active than the original drug. In contrast, phase 2 conjugation reactions attach one of the body's own molecules. This not only makes the drug water-soluble, but almost always, it completely inactivates it, switches it off for good. So who are these workers, these enzymes that are carrying out these critical phase 1 reactions? Well, it is time to meet the single most important family of enzymes in all of pharmacology. You need to remember this name, the cytochrome P450 enzymes, or as we all call them, the CYP enzymes. Think of them as the absolute workhorses of drug metabolism. This huge superfamily of enzymes, living mostly in the liver, is responsible for breaking down the vast majority of medicines we use today. And what's amazing is that even within this massive family, just a handful of them do most of the heavy lifting. Just look at this chart. A single subfamily, CYP3A4, and its cousin 3A5, is responsible for metabolizing nearly half of all clinically used drugs. That's a staggering number. Then you have other important ones, like CYP2D6 and the CYP2C family, and they handle most of the rest. Now, this metabolic factory in the liver, it doesn't always run at the same speed. Its activity can be ramped up or it can be slowed right down. And these changes in speed can have enormous consequences for our patients. A great way to think about this is like the pedals in a car. Some drugs or even some foods can act as an accelerator. We call this enzyme induction. They tell the liver, hey, make more enzymes, work faster. So the metabolism speeds up, the drug gets cleared out too quickly, and its effects can disappear. Then other things act like the brakes. This is enzyme inhibition. They block the enzymes, the factory line slows to a crawl, and the drug levels can build up and up, risking serious toxicity. Let's look at a classic real-world example with our superstar enzyme CY3A4. Imagine your patient is taking the cholesterol drug simvastatin. Now, if you also give them rifampin, a powerful inducer and accelerator, their metabolism speeds up like crazy.
This Simvastatin gets chewed up and removed so fast its levels will plummet. The drug might just stop working. On the other side, if you give them an antifungal like ketoconazole, a strong inhibitor, the brakes, metabolism slows right down. Simvastatin levels can skyrocket, putting the patient at risk for severe muscle toxicity. This is exactly why you must always check for drug-drug interactions. Okay, so our drug has been biotransformed. The liver did its job. It's converted the fat-soluble molecule into a water-soluble one. Now it's time for the final exit.
And the primary exit route is the kidney. But as this diagram shows, the kidney isn't just some simple filter. No, it's a highly sophisticated processing unit that uses 3 key mechanisms to decide what stays and what goes. Here's how it works. First, the drug is filtered out of the blood. Second, special pumps can actively secrete even more of it into the urine. But the third step is the most important one. You see, as water gets reabsorbed from the urine back into the blood, a fat-soluble drug could easily slip back in, too. But our new water-soluble metabolite? It's trapped. It can't cross back over the wall, so it's flushed out of the body for good. And this isn't just a textbook concept. We use this principle to save lives. In the emergency room, if someone comes in with an overdose of an acidic drug like aspirin, what do? We give them sodium bicarbonate to make their urine more alkaline. This ion traps the drug in the urine, preventing it from being reabsorbed and dramatically speeding up its removal from the body. It's a beautiful clinical application. But before we finish, there's one last twist in the tale. Sometimes, a drug metabolite that's been excreted into the gut through bile can be reactivated by the bacteria living there. It then gets reabsorbed back into the blood and sent to the liver for another pass. This is called enterohepatic cycling, a recycling loop that can make a drug's effect last much longer. So let's just quickly recap the whole story. We started with a fat-soluble drug that the body can't easily get rid of. The liver solves this problem with its 2-phase metabolism, with the CYP450 enzymes as the star players. We saw how this whole process can be sped up or slowed down by other drugs, leading to potentially dangerous interactions. And finally, the kidneys trap this new water-soluble molecule and make sure it exits for good in the urine. So, I'll leave you with this final thought. A drug's effect isn't just about the dose you prescribe. It's about this incredibly complex, variable journey it takes inside the body. This journey is affected by other drugs, by our own genetics, and so many other things. So the real question is, what does this mean for how we treat each patient? If everyone's internal factory is different, how do we start treating them as unique individuals they are? Thinking about that is the first step toward becoming a truly great physician. Namaskar, everyone, and welcome. As a doctor, probably the most important decision you will make every single day is the dose of a drug. You give too little and it's useless for the patient. You give too much and you risk making them even sicker. Getting that dose perfectly right, well, that's an art. But it's an art that is built on some very solid science. So today, let's get into the science behind this beautiful art. So here's our plan. We'll start with the body's cleanup crew. Then we'll figure out how to score their efficiency with something called clearance. We'll look at the 2 big rules they follow, first order versus zero order. Then we'll talk about the superstar of kinetics, the half-life. After that, we'll see how we reach a nice, stable level, or plateau. And finally, we will put it all together for some truly smart dosing. Ciao, let's begin. Okay, first things first. We give a patient a medicine. It goes inside, it does its job. But what happens after that? It can't just stay there forever, right? It has to be removed. This whole process is called elimination. And you can think of it as the body's essential 24/7 cleanup service. And trust me, without this service, every medicine we give would eventually become a poison. So, I want you to really think about this question. How does the body actually do it? Well, you know the basics. Metabolism, mostly in the liver, and excretion, mostly by the kidneys. But why is this the most important question? Because the answer to this tells you everything. It tells you how much drug to give, how often to give it, and most importantly, how to keep your patient safe. Everything we do in dosing starts right here. Now, let's get into our first big concept. If the body has a cleanup crew, we need a way to measure how good they are at their job, Henna. We need a number. And that number is called clearance. Just think of it as an efficiency score for the body's entire drug removal system. Now, the textbook definition, it sounds a bit complicated, doesn't it? Theoretical volume of plasma. All right, let's make it simple. Imagine your kidneys and liver are like a super advanced water purifier for your blood. Clearance just tells you how many milliliters of blood that purifier can make 100% clean of the drug every single minute. It's not an amount, it's a rate of cleaning, measured in volume per unit of time.
And look, this picture makes it crystal clear. See, the blood going into the organ has a drug concentration of 10 micrograms per milliliter? Now our organ, our purifier, is removing 500 micrograms of the drug every minute. So simple maths. To get 500 micrograms out, how much blood did we have to clean completely? Just divide 500 by 10, and you get 50 milliliters. So the clearance is 50 milliliters per minute. See? It's a volume of blood that's been cleaned, not an amount of drug. Very important distinction.
Okay, so the body is cleaning the blood, but does it always work at the same speed? Well, no. It generally follows one of two main rules or systems, and knowing the difference between these two is absolutely critical if you want to avoid making a drug toxic. We call them first-order and zero-order kinetics.
So for most drugs, it's first order. Think of it like a factory with unlimited workers. The more drug that arrives, the more workers show up to clear it. A constant fraction, like say 10% of the drug, is removed every hour. Easy. But for some drugs, the system gets saturated. It's like the factory only has 2 workers. No matter how much drug you send, they can only work at one fixed speed. This is zero order. A constant amount is eliminated, and this is where things can get very dangerous.
And this graph shows you exactly why it's so dangerous. Look at the first order line. You double the dose, you double the plasma level. It's predictable, it's linear, it's safe. But now look at that zero order curve. Once those factory workers are overwhelmed, even a tiny increase in the dose can cause the drug levels to just shoot up into the toxic range. Phenytoin and even alcohol are classic examples. This is a curve you must respect and fear. All right, let's move on to what I think is the single most useful, most practical number in all of clinical pharmacology, the half-life. If you want to know the story of a drug, how long it's going to stick around, how often you need to give it, the half-life tells you everything. Just look at this graph. When you give an IV drug, you see this first sharp drop, the alpha phase. You know, that's just the drug spreading out, getting distributed into the tissues. We're not so interested in that. We're interested in the second, slower part, the beta phase. This is the actual elimination. And the half-life, or T-half, is super simple. It's just the time it takes for the drug concentration to fall to 50% of what it was during this phase. And this leads us to a magic rule, a practical rule you must remember for your entire career, the rule of 5. After 1 half-life, 50% of the drug is gone. After 2, 75% is gone. After 3, 87.5%, you see the pattern. By the time you get to about 4 or 5 half-lives, over 94% of the drug has been eliminated, and for all clinical purposes, we can say the drug is now gone from the body. But think about it. Patients almost never take just 1 dose of a medicine, do they? They take it every day or twice a day. So what happens then? Well, the drug starts to build up, it accumulates in the body until it reaches this stable level plateau. We call this a steady state. This graph shows it beautifully. It's like you're filling a bucket that has a small hole in it. With every dose, you add more water, and the water level goes up. But as the water level gets higher, it starts leaking out faster because of the pressure. Eventually, you reach a point where the amount of water you're adding is exactly equal to the amount that's leaking out. The water level becomes stable. That's your steady state. And how long does it take to get there? You guessed it, our magic number again, about 4 to 5 half-life. Acha. So now we have all the pieces of the puzzle, right? We have clearance, half-life, steady state. So how do we put all this theory together to become not just a doctor who writes prescriptions, but a master clinician who doses perfectly? Look, in an emergency, say a patient has a life-threatening infection, you can't wait 4 to 5 half-lives for the drug to work. You need it to work now. So what do? We give a large initial loading dose to quickly fill up the body's volume of distribution and get to our target concentration fast. And then, once we are there, we switch to smaller, regular maintenance doses, just to replace the drug that the body is clearing out. And remember this, loading dose is all about volume, but the maintenance dose is all about clearance. But here's the thing, every patient is different. The textbook tells you the average clearance, but your patient is not an average. So for some very tricky drugs like digoxin with the low safety margin, or in patients with kidney failure, we can't just follow the book. We have to do something called therapeutic drug monitoring, or TDM. We literally measure the level of the drug in the patient's blood to make sure we're in that sweet spot, safe and effective. So you see, these principles we've discussed, they are the foundation of pharmacology. They are timeless. But of course, technology is always moving forward. So what does the future look like? How can we use these same rules in even smarter ways?
Well, the future is all about precision and control. Look at this diagram of a controlled release system. A normal tablet gives you a big spike of drug, then it falls. It's a roller coaster. These clever new systems release the drug slowly and steadily all day long. They avoid those peaks and troughs. The results? A much smoother, more constant drug level, which means better effects and fewer side effects. We are basically building our knowledge of kinetics right into the pill itself.
So there you have it. Clearance, first, and zero order, half-life, and steady state. Believe me, these are not just concepts for your exams. These are the fundamental rules of the game that you will use every single day to treat your patients safely and effectively. So the only real question left is, now that you know the rules, how are you going to apply them to dose your next patient perfectly? Think about that. Thank you.